Imagine trying to run an entire bustling metropolis. You've got skyscrapers, subways, millions of street lights, all of it demanding power at the exact same time.
Right, a massive electrical grid.
Yeah. But now, try to power that entire grid using a single AA battery.
Oh, wow. Yeah, that's not going to work.
No, it's not. And that physical bottleneck, that absolute disparity between the energy required and the infrastructure available to deliver it, well, that's essentially the defining crisis of artificial intelligence right now. Welcome to the deep dive.
Glad to be here.
So while everyone is out there talking about the massive new GPUs powering AI, our mission today is to, look underneath the floorboards. We are mapping out the actual physical reality of the AI data center. Because without some pretty radical overhauls in power delivery and optical data transfer, these billion-dollar chips are, frankly, going to turn into molten slag.
They literally will. I mean, the sheer physics of what happens inside these facilities is forcing a complete architectural rewrite of the digital world.
Right.
And to map this out for you, we're pulling insights from some incredibly detailed technical sources. Specifically, we're looking at deep dive financial and engineering analyses from the Stock, Croc, and Serenity substacks, along with corporate press releases and some insider supply chain mapping.
Yeah, the sources are dense, but they're tracking a massive shift, what they call a physics mandate. And it all starts with something known as the 54-volt problem.
Yeah, the 54-volt problem.
Yeah.
So legacy data centers, they were designed for traditional servers, drawing maybe, 100 watts.
Which isn't much.
Exactly. So in that environment, distributing power at 54 volts made perfect sense. But today, a single AI chip, like NVIDIA's 1400-watt GPUs, requires so much power that those 54-volt systems simply can't cope.
Okay, wait, let's unpack this really quick. I want to use a water pipe analogy for a second. If we think of voltage as water pressure and current the amps as the actual volume of water, if we have low pressure but we need massive power, we have to push a staggering volume of water through that pipe, right?
That's exactly it. And the consequence of that is what engineers call a copper absurdity. To handle that sheer volume at 54 volts, the copper wiring has to be massively thick so it doesn't just melt.
Right, because of the resistance.
Yeah. A single 1 megawatt AI rack running on 54 volts would require nearly 200 kilograms of copper.
Oh, wow. That's insane.
It's a literal barrier to construction. You simply cannot build a data center out of solid copper tree trunks.
And beyond just the sheer weight and space, there's the heat.
Oh, absolutely.
Because heating losses scale with the square of the current. So if you push 10 times the current through a wire, you get 100 times the heat.
Which creates a cascading failure. You end up spending millions just to cool the wires before you even start cooling the actual processors.
Right. So the industry's solution to this physics mandate is to force a shift to an 800-volt DC architecture. By increasing the voltage, the pressure the current drops.
And then heating losses plummet. The copper requirements basically collapse by like 45 to 50%.
And it improves end-to-end efficiency by, 5 to 7%?
Yeah, around there. Which, at the gigawatt scale of these facilities, saves absolute fortunes.
But there's a catch, isn't there? Because pushing 800 volts through standard silicon chips will basically destroy them.
It completely destroys them. The atomic structure of standard silicon just can't handle it. The breakdown voltage is too low, so the electrons are forced to jump their designated paths. And you get this uncontrolled leakage.
So the entire silicon foundation of power management has to be ripped out. We need a completely different material to handle this kind of power.
Exactly. And this is triggering a massive supply chain battle that analysts are calling the wide band gap war.
Right, the battle between gallium nitride, or GaN, and silicon carbide, or SiC.
Yes. So traditional silicon has a narrow band gap of about 1.1 electron volts. It fails entirely around 600 volts. But GaN and SiC, they have wider band gaps, around 3.2 electron volts.
I always think of the basement and highway analogy here, like electrons jumping from the basement to the highway to conduct electricity.
That's a great way to picture it, yeah.
With silicon, the jump is easy, but at 800 volts, it's just too much energy and the electrons blast right through.
Right, but GaN and SiC act like a much higher rated circuit breaker for that 800-volt grid. They don't leak or break down.
So what does this all mean, though? Both GaN and SiC have wide band gaps. Why is there a war between them? Shouldn't one just mechanically prove superior and win?
Well, you'd assume that, but it's really a horses for courses reality. A data center has distinct stages of power conversion. Silicon carbide, SiC, is basically the diesel engine.
Rugged, heavy duty.
Exactly. It handles extreme high voltage and high heat, so it dominates the facility perimeter, which is layer P0. This is where grid power enters the building.
And even within that layer, there's a war within a war, right? Between trench and planar seeking.
Yeah, that's huge. Older planar designs move current horizontally across the chip surface, which creates resistance. But companies like Infineon and ROHM are winning because they carve vertical canyons, the trench design, straight into the chip.
Which allows the current to flow straight down, lowering the resistance and the heat.
Exactly.
Okay, so if size is the diesel engine at the perimeter, what is GaN doing?
GaN is the petrol car, the speed king. It handles mid-conversion, taking power from the rack to the board. It switches on and off at lightning-fast speeds, approaching 1 megahertz.
And the secondary effect of that speed is what really matters, right? Because it allows the heavy magnetic components to shrink dramatically.
Yes. You can take an entire cabinet of power gear and compress it into a module the size of a paperback book.
Which is vital because space inside the rack is the most premium real estate on Earth.
Exactly. So, okay, we've safely brought 800 volts onto the board. But as we get literally inches away from the actual GPU, we hit arguably the most terrifying engineering hurdle yet.
Right. The 1500 amp wall.
Yes. Layer P3, the point of load. To power a 1400-watt chip at less than 1 volt, you have to push roughly 1500 amps of current into a piece of silicon smaller than your thumbnail.
Which is enough current to cold start, like, 30 semi-trucks simultaneously.
It's staggering. And if you try to move that much current laterally across a copper circuit board, even for an inch, the copper acts like a literal fuse.
It just melts.
It completely melts.
Yeah.
Lateral power delivery fails. So the only solution is vertical power delivery, or VPD.
Mounting the power modules directly underneath the processor.
Right. You punch the current straight up into the silicon using 3D stacking.
But wait, if a company figures out how to do this, like Alpha and Omega with their top clip thermal designs or Vickers with their patents, don't they just own the market forever?
You would assume the moats are deep. But in this sector, moats are like thin ice. They reset every 12 to 18 months with each new GPU generation.
Wow.
Yeah. Take MPWR, for example. Back in 2023, they looked completely unassailable, holding the primary socket for NVIDIA.
But then the Blackwell architecture happened.
Exactly. During thermal validation for Blackwell, MPWR's components developed localized overheating issues. Within months, they lost that primary socket to Infineon and Renesas.
So loyalty means nothing if you can't survive the heat.
Nothing. Thermal survival is everything.
Which points out the recurring enemy in all of this heat. Moving electrons through copper naturally creates resistance and heat. So to solve the data transfer heat problem, we basically have to abandon electrons entirely.
We do. The industry is building what analysts call a glass city running on photons. This is the photonics supercycle.
Shifting to optical transceivers, using pulses of light instead of electricity to move data so you don't generate that crippling heat.
Exactly.
But to do that, you need highly specialized lasers. And our sources point to a major choke point forming around a relatively unknown Swedish company called Sivers Semiconductors.
Right. Because in April 2026, Jabil, a massive global manufacturer, announced a next-generation 1.6T linear receive optical transceiver, or LRO, and is built entirely around Sivers DFB lasers.
And Jabil wouldn't risk that on a small supplier unless the architecture was leaps and bounds better than legacy giants like Lumentum, right?
Exactly. It's all about power efficiency. Jabil's architecture requires only about 11 kilowatts for a 1.6T profile. That is a 2.5 times lower energy footprint. Hyperscalers are begging for that.
And Sivers also has their NP100 platform, the etched facet design.
Yeah, that solves a massive manufacturing bottleneck. Traditionally, to make a laser, you have to physically break the wafer, package it, and then test it. If it doesn't work, you've wasted millions.
But Sivers etches the mirrors directly onto the wafer, so they can do full optical testing on wafer before anything is diced up.
Exactly. The cost savings are immense, which is why Jabil essentially stated that demand for these 1.6T LROs is essentially uncapped.
Uncapped demand, meaning they'll sell every unit they can make just to keep up with organic growth. But here's where it gets really interesting. If demand is uncapped, who exactly is buying all these lasers?
Right, because these supply chains are buried under NDAs. But the Serenity Substack used open source intelligence, OSINT, to map it out.
Yeah, so Sivers publicly stated they have a Fortune 100 U.S. customer requiring 50 million units a year for a highly specific 135 wavelength architecture.
And when you cross-reference that, there's likely only one company in the world selling 50 million consumer wearables a year requiring that.
Yeah.
Apple, for the Apple Watch.
Wait, really? A consumer watch needs a data center grade, 135 wavelength laser array.
It does for non-invasive health monitoring, specifically blood glucose tracking. You need to fire dozens of highly precise wavelengths of infrared light into the tissue and measure absorption.
Oh, wow, like Raman spectroscopy.
Exactly. Sivers lasers provide that microscopic stability.
That is wild. But the USINT mapping also shows Sivers expanding aggressively in the core data center market, right?
Yeah, analysts looked at the back-end HTML code for IR Labs, a major player in co-packaged optics.
Where they put the laser directly onto the processor package.
Right, and the code showed the competitors Lumentum and Mecom were scrubbed from IR's site, leaving Sivers as the primary laser supplier.
And because Sivers is Swedish, they're a neutral arms dealer. They map to U.S. hyperscalers via Marvell and AMD, and Asian hyperscalers via ONET in China.
They're capturing both sides, and Jabil's statements confirm that mass production is pulling forward. Quals are finishing up now, meaning revenue hits in anywhere from 3 to 10 months. So mid to late 2026.
Okay, so let's summarize this incredible journey for you. The life cycle of a data center is just a gauntlet of extreme physics. It starts at the grid with 800-volt silicon carbide transformers,
Then it races through gallium nitride speed switches.
down to a 1500-amp vertical power delivery system stacked right beneath the GPU.
And finally, it bursts out as precise pulses of light fired by Sivers lasers across the glass city.
It really is a miracle it doesn't all just evaporate.
It is.
But there is one final mind-bending application of this source material we want to leave you with. We just spent this entire deep dive talking about data centers on Earth.
Right. But the exact same wide bandgap technology that did Zacchaeus and GAN fighting heat in AI is secretly the power backbone of the low Earth orbit satellite economy.
Wait, like Starlink?
Exactly. And it's not because of heat in space, it's because the atomic bonds in GAN and SEER are so strong that they are naturally radiation hardened.
Oh, wow. So they don't need heavy lead shielding to survive space.
Right. Standard silicon would just be corrupted by cosmic rays. But GaN and CCAS survive unshielded, which saves massive amounts of payload weight.
So the exact same physics mandate keeping an AI from melting down is currently floating 500 kilometers above your head, surviving the radiation of space.
From the basement of a data center to the vacuum of orbit, it's the universal solution.
That is unbelievable. Next time you ask an AI a question or check your smartwatch or use satellite internet, think about the extreme physical architecture operating invisibly in the background. Thank you for joining us on this deep dive into the hidden layers of our digital world. Keep questioning the physical realities behind the screens, and we will catch you on the next deep dive.